Okay. Now, when we speak of crystallization, it could be as simple as forming solid particles from a homogeneous phase. Okay? Or it could be as detailed as it's the solution being concentrated, and the manner of concentration is usually done by the process of cooling until the solute that is present in our homogeneous solution becomes greater than its solubility at that temperature. So its concentration becomes greater than its solubility at that particular temperature, and as such, it comes out, or other terms that could be used in here is that it precipitates out of the solution, forming what we call the crystals of pure solute. So in here, the process that is done in order for your solids to precipitate out of their solution is cooling. Now, it could also be a simple case of cooling, or it could be a case of evaporative cooling. Now, we can also view crystallization as a solid-liquid separation process in which there is mass transfer of the solute from the liquid solution, and it's being transferred to a pure solid crystalline phase. And that's the process of crystallization. So this is mass transfer from the liquid phase to the solid phase. Now, crystallization may occur as the formation of solid particles in vapor, and that is in the case of snow formation. So your crystals were formed from vapor, and the usual case is the solidification from a liquid melt. And this is the thing that is, this is the technique that is used, or the processing that is used in forming or in manufacturing large crystals. Okay? And also we can say that crystallization may occur as crystallization from the liquid solution as the usual case. Now, in crystallization, we are not only interested with the quantity, with the yield and the quality, the purity of our crystals, but more importantly, we are also concerned with their sizes and shapes. So it's very important that they come up with the uniform, or we come up with the uniform sizes and shapes of crystal. Why? So the big question is, why is it required that the sizes be uniform? So size uniformity is desirable too. So these are the reason behind that. To minimize caking in the packaging later, for ease of pouring, and for ease in washing and filtering if your crystals are to be processed further, and for uniform behavior when they are used. So it is important that the sizes of our crystals be uniform. Primarily in the case of packaging, this particular concern in caking, and in the case of pouring, and in the subsequent processing of your crystals during washing and filtering, it is very important that they are of uniform size. Now, when you speak of crystallization, there are two terms actually that comes into mind. So we have the crystals and the magma, where these crystals came from. So when you speak of crystals, you have studied this in detail in your material science. It is a solid composed of atoms or ions or molecules which are arranged in an orderly and repetitive manner. So in terms of structure, it's very, shall I say, balanced. It's orderly. The structure is orderly and organized. As referred to in here, it's a highly organized type of matter. So atoms, ions, and molecules here are located in three-dimensional arrays or space lattices. So if you're going to look them in under the microscope, if you're going to look at these crystals, they are composed of ions or atoms located in three-dimensional arrays. Now, they appear as polyhedrons having flat faces and sharp corners, referring to these crystals. And if we think of crystals belonging to a particular material, so they are made of the same material, or they are the crystals coming from the same material, the angles between the corresponding faces of all crystals are said to be equal and are characteristic of that particular material. Now, I've mentioned about the magma. So when we associate, when we talk about crystallization, we not only talk about crystals, but the magma. So in industrial crystallization from solution, that is forming crystals from solution, it is the two-phase mixture of mother liquor and crystals of all sizes which occupies the crystallizer and is withdrawn as the product. Or from the magma, we produce our pure crystalline solids or our crystals. Now, if we have to represent in a schematic diagram the crystallization process wherein simple cooling happens, so this is what happens. You have your feed introduced into your crystallizer unit and it undergoes cooling. And in the process of cooling, we, shall I say, we induce the formation of crystals. So solids tend to precipitate out of the solution, which enables us, when it is already separated in the centrifuge, separate the liquor from the crystals. But this magma is the main product of your crystallizer and it's being processed further in centrifuge to separate the solids, the crystals, from the mother liquor. If you will do your on-the-job training come this summer of next year, and if you come and if you'll be fortunate enough to be allowed to go to sugar crystals, you will see the crystallizers and you will see the centrifuge that processes the magma coming from the crystallizers. So this is a case of the formation of crystals induced by a simple process of cooling down your feed in a crystallizer. So these crystallizers class in its simplest forms may look like cylinders, cylindrical tanks that are oriented in horizontal manner, and it is, shall I say, divided into two parts. So it's a half cylinder, and in that half cylinder, you have rotating coils where cooling water is flowing in the process, inducing cooling of your feed in the crystallizer. So once cooling is induced, more crystals are being formed and growth is, shall I say, enhanced. And as such, when later on this magma is discharged into the crystallizer, they are now, or they can be readily separated into mother liquor and crystals. Now, there are other cases of crystallization in the industry, which is vacuum crystallization, wherein there is a certain amount of water being evaporated from the solution, from the feed that was processed in the crystallizer. Again, still with the same objective of concentrating the feed in the crystallizer and inducing the growth of solids, because then your solution will have more solids present than the liquor, or shall I say the liquid that is present on it. So that will induce faster the growth of crystals. And then when time is right, this magma is again introduced into the centrifuge to separate the mother liquor and the crystals. Now, in industrial crystallization, crystallization can be used, number one, in the production of crystals. So really in the production of whatever crystals that may be. In the purification of solids. So if we want to purify a particular solid from contaminants present on it, then it can be processed using crystallization, melting it and then separating the impurities and then separating, in the end, you will have your pure solids. Okay, then we also have recovery of solids. If we want to recover solid from a particular solution, whenever it is a part of, or it is a component of crystallization, can also be used. So three possible purpose of crystallization in the industry. Now, we have production of salt. These are salt farmers from Las Piñas City. So this is how they harvest the salt. Of course, you can see that the salt are formed due to evaporation of water. So there's no need for any industrial equipment here. The process of evaporation is done by simply exposing the seawater to the heat, under the heat of the sun. and then that will produce already your salt. Or the usual case is in the production of salts inside tank crystallizers. It could be done that way, or it could be done in the case of the sugar production. Initially, your cane juice is being cooked in these very high evaporators. Of course, the purpose is to concentrate it. And then from these evaporators, the solution is dispensed down into the crystallizer units below. The crystallizer induced the formation of the crystals and then separated through the centrifuge, the use of the centrifuge. Now, we also have production of silicon crystal wafer in the case of our friends, the ECEs. They use this. The silicon is where those, shall I say, information that needs to be, shall I say, placed in a particular electronic gadget. So it's where they etch it. So the term that they use is they etch it on those information, or even the circuitry is etched on silicon crystal wafer. So from the term itself, silicon, so your wafer is made up of silicon crystals. So the process of the formation of the silicon crystals is illustrated here. So it need not be always class that when we speak of crystallization, it's something in which it's, we produce something that is powder. It could be something as this one, your wafer, silicon crystal wafer. Okay, I think my video here will not work, but we'll just proceed. Now, in the case of the use of crystals in nanotechnology, so you have a sample here. This is a particular device that transfer energy from nano-thin layers, very thin, nano-thin layer of quantum wells to nanocrystals above. So all nano materials. So nano-thin layers here and nanocrystals above. In the process, causing the nanocrystals to emit visible light. So that's one application of the crystals in the, of nanotechnology rather, and the formation of crystals in our day-to-day life. So I think these are being used in the design of the things that we are using every day, or we are some of the things that are being used by some of us every day. Now we go to the real thing of what happens during industrial crystallization. And speaking of the uniformity of the size of crystals later, not only the quantity and the purity of the crystals being important. So it could be something like this. It could be as diversified and varied as this, their sizes, their shape. And the behavior of materials are actually a function of this particular size and shape of crystals. So mainly physical, chemical, mechanical, and rheological properties of solid materials depend on the grain size and the size and the shape rather of these grains, or shall we call it crystals, that could be also in the form of that will form the grains of our material. So why are this particular grain sizes and shape very important? So in the case of pigments, I think this is very self-explanatory. In the case of pigment, sizes are something that is really under quality control. Pigments for paintings, for paints, catalysts that are used in chemical reactions, pharmaceutical products, food products, even more so materials used in electronics. So they undergo intensive quality control. That way the crystal wafer that is being used, especially in electronics, does not have any defects. Okay, so actually they are employing also chemical engineers in that particular part of the process wherein they need quality control. Now, the particle size, distribution, and particle shape of a solid product are essential criteria for its commercial quality. So more so on the size and the shape, the uniformity of the size and shape of the crystals being produced. So to this aim, it is necessary to define and perform the necessary physico-chemical transformation, the reactor type. So there has to be a proper design for the reactor that will facilitate such, and the operating conditions in the formation of these particular crystals. Now, when we speak of crystallization to happen, your solution has to be in what we call saturated condition or supersaturated condition. Otherwise, we won't have the growth of crystals, or we won't even induce the growth of crystals. So when we speak of saturated solution, now from thermodynamics, we learned this in thermodynamics, it's a solution that is in thermodynamic equilibrium with the solid phase of its solute at a given temperature. Or some references will even discuss this as at a particular temperature, this is the highest maximum allowable solid content that your solution can carry. And that particular condition is the saturated condition. And we refer to the solution as the saturated solution. Now, once we deviate from this maximum amount of solute that your solution can carry at specified condition, we have what we call as the supersaturated solution. It carries with it already more solute than what it can carry at normal condition, or at we call that at equilibrium saturation condition. So then your solution is referred to as a supersaturated solution. It has more solute that it can carry at saturated condition. Now, in speaking of supersaturation, so saturation, it's something like your solution already has reached the maximum solute concentration. We go beyond that, it's supersaturated. Now, how do we express the supersaturation of a particular solution? Now, by the way, the main reference material that is being used in this set of slide is, what is this? It's not Jean Couplis, it's not McCabe, but it's a different source. I forgot the name. I'll give you the name of the author later of the book. It's a unit operations books in volumes. It has different volumes for a different type of unit process. Colson, this is taken from the unit operations by Colson. So expressing the degree of supersaturation, Richardson. It's Colson Iho, Drexel. I got this from Colson. Okay, it has several volumes. Going back to what I'm saying, so when we speak of supersaturation, it's represented as delta C. It simply is a measure of how much is your solution concentration, or how much did your solution concentration went beyond the equilibrium saturation value, or how much has it, shall I say, if it's referred to a different term in process control, it has already overshoot, it's overshoot already the equilibrium saturation value. So we simply take the difference of these two, and it's defined in here anyhow. The solution concentration, whatever that may be, and we subtract from it the equilibrium saturation value. Your degree of supersaturation can also be expressed in terms of the supersaturation ratio. This time, it's more straightforward, direct, because you simply have C over the C asterisk. Whatever is the solution concentration, we compare it to the equilibrium saturation value by division. Now, we also have another way of expressing it is the relative supersaturation. So how supersaturated it is, so how much has it overshoot the saturation value, and we compare it to that same thing. So the difference, the delta C, the degree of supersaturation divided by the saturation value is your relative supersaturation. Or if you have already the supersaturation ratio, you just subtract 1 from it. That's the relative supersaturation already. Now, there's a note here that solution concentrations may be expressed as the mass of an hydrate, your solute without the water that it contains, over the mass of your solvent, or as mass of hydrate, your solute with the water on it, divided by the mass of free solvent. So it could be either of these two. So we have to make sure that if we started with a concentration of mass of anhydrate over mass of solvent, let it be like that in all your computation. Or if you started with this, mass of hydrate over mass of free solvent, then let it be like that. Not that you will express your concentration in terms of mass of anhydrate over mass of solvent, and then later on in your other computations, you will use this manner or unit for your concentration. So let it be uniform. So the choices of the units that we will use for our concentration of solution may affect our relative supersaturation and supersaturation ratio. So it will affect the S that we have here and our relative supersaturation. Now, we have this sample problem number 1. It will simply make use of the formula, the 3 formulas that were introduced here. And in this sample problem, you are given a 293 Kelvin supersaturated solution of sucrose containing 2.45 kilograms sucrose per kilogram of water. Now, if equilibrium saturation value is 2.04 kilograms sucrose per kilogram water, what is the supersaturation ratio in terms of kilogram sucrose per kilogram water and kilogram sucrose per kilogram of solution? So in this case, class, the manner of expressing the concentration is anhydrate over solvent. So kilogram sucrose per kilogram of water. So if you adhere to the set units, then let it be your set units 2 and 2, just for this problem only. Okay, now we'll solve this problem. Let me transfer to the Jamboard. Because I can't find it. Wait, just. Okay. Okay, so we'll write down our given information here, what the problem gives us. So this is our first sample problem. We're not yet here to design crystallizers. We're simply going to employ the 3 formulas that were used in expressing the concentration of a supersaturated solution. So based on our problem, the problem that I read to you, I will not go back to the problem anymore. I just write the given information here. You're given a sucrose solution at 293 Kelvin. So that's the temperature, and it is said to be a supersaturated solution. So the concentration of the supersaturated solution is 2.45 kilograms sucrose per kilogram of water, which is your solvent. Then it was mentioned that the equilibrium saturation value at the indicated temperature, so that's your C asterisk, is 2.04 kilograms sucrose still per kilogram water. Okay, so you are required for this particular problem to determine the supersaturation ratio. So the S, so in 2 sets of units. So one is in kilograms sucrose per kilogram water, and another one is kilogram sucrose per kilogram of solution. The first one is very easy because you have everything there. So all you have to do is divide. So S in kilogram sucrose per kilogram water will be 2.45 based on this one divided by 2.04. And you will have here an answer which is 1.2. So this is kilogram sucrose per kilogram water. Okay? Kilogram sucrose per kilogram water. Now, if it's in terms of kilogram sucrose per kilogram of solution, in this case, it's very simple because you simply have to work on the values that you're provided with. How will you work your way through the given information? So this is the given. How will you work through this one so that you will have kilogram sucrose per kilogram solution? What will you do? Anybody? This one is okay. We're working on the same unit as the problem gave us, set of units. What about the other one? What do we do? Our unit here for the second is kilogram sucrose per kilogram solution. Your two concentrations, the one at supersaturation and the one at equilibrium saturation, is having units kilogram sucrose per kilogram water. Problem requires you to express it in kilogram sucrose per kilogram solution. So what would you do then? Now, some of the problems that you will be encountering probably in the board exam may be something that is very new, but if you know how to do dimensional analysis, work your way through or manage your given information to come up with the desired set of units for the unknowns in your product, then it's good for you. So in this case, I'm asking you now, how will you determine that very simple question, but this time having a different set of units? What would you do with these original values? Okay, somebody wrote in the chat box, Drexel. So you will have C over C. Is this C over C plus C asterisk? Okay, I'll write it, Drexela. Please see the chat box. So Drexel is suggesting that we determine, you mean all your concentrations will be expressed in terms of C over C plus C asterisk. Remember, class, that we did not cancel units here. It's just that the units of the concentrations here are expressed in terms of kilogram sucrose per kilogram water. Now, the required information is asking you to determine the same supersaturation ratio, but this time you will use the unit kilogram sucrose per kilogram of solution. It does not mean that the resulting unit of this 1.2 value is this, because we don't cancel units. It's not that, but rather you got your value by working on set units, which are kilogram sucrose per kilogram water. Now it's asking you to work on set units, kilogram sucrose per kilogram solution. How will you find it? Assume mass of water. What's the mass of water then? Drexel? Based on the given concentration values, what's the mass of water? Actually, you need not assume, it's there. What's the mass of water? 1. Very good. It's 1. Very good. So if I intend to find so I'll change this one, the supersaturation value in which my units will be kilogram sucrose per kilogram of solution, what do I need to do? What do I do? I will, John Albert, you will have C over C plus 1. Very good. Not only for your C, but you do the same for your C asterisk. So meaning, class, you will find a new C in which you will have 2.45, just like one John Albert is suggesting, over 2.45 plus 1. Where did I get this one in the first place? Isn't it this equal to 1? So for every 1 kilogram of water, you have 2.45 kilograms of sucrose. So that's what you're applying here. That way, you will have a unit, which is, by the way, the answer for this is 0.71. Your unit here now is kilogram sucrose per kilogram of solution. Your denominator now is your sucrose plus your water, so it's kilogram solution. You do the same with the equilibrium saturation value. Okay, so you do the same for your C asterisk. So your C asterisk would be recomputed so that the unit could be changed. So it's 2.04 over 2.04 plus 1. So you'll be getting a value here, which is 0.67. So it's kilogram sucrose per kilogram of solution. Now you can determine the supersaturation using this set of units already for your C's. The concentration, the supersaturation concentration, and the equilibrium concentration. So in this case, I will have now 0.71 over 0.67. So this gives you 1.05. Okay? The supersaturation ratio of 1.05. Now, if you're going to compare it with the set units kilogram sucrose per kilogram solvent, your supersaturation value is 1.2. In here, it's just 1.05. So you get a lesser value of supersaturation, it's just but the number, when the unit is changed. So it really matters on what particular set units you will use. Okay? Do you have any question with this? So very simple illustration on how we use the formula. The three formula in here, we just simply use the supersaturation ratio. If there aren't any questions here, let us proceed to the next slide. Okay, let's see. So that's the sample problem 1 that we determine the unknowns. Oh, by the way, this is your sample problem number 1. Now, in terms of, so it's not that it's the unit, but rather your units, the units of the quantities that you are working on are in the first one, kilogram sucrose per kilogram water, and in the second one, kilogram sucrose per kilogram solution. Now, let's go to the proper way of illustrating a vacuum crystallizer, because this is the usual case in the industry, although there are still industries that are still using the simple cooling process. In us here, even the sugar centrals are just using the simple cooling process. So we represent our feed as F. This is the solid content of our feed, XF. This is its enthalpy, and this is its temperature. Now, if a certain amount of water is vaporized, so it's represented as V, its enthalpy is H sub V. Your magma is represented as M, and it has this representation for solid, enthalpy, and temperature. From your magma, we have the mother liquor represented as L, and its solid content and enthalpy representations here, X and H, and same thing with the crystals. So this is how we represent it. Our referring to our crystallizer. So when you write your problems later on, just affix the quantities that are provided in the problem in this schematic, in this particular illustration. Now, when we speak of industrial crystallization, it's important that we know the yield. Okay, when we speak of the yield, it has something to do with the quantity of crystals produced. So the yield of crystals produced by a given degree of cooling, in this case, may be estimated from the concentration of the initial solution, that is the concentration of your feed, and the solubility at the final temperature, or that is the concentration of your solution now once inside the crystallizer as it is being processed. So the concentration inside the crystallizer and the solubility are all the same thing. So if the problem refers to the concentration of your solution inside the crystallizer, or given the operating temperature or pressure of your crystallizer, this is the solubility of your crystals. That is also referring to the concentration of your solution inside that particular crystallizer. So final concentration C2 and your solubility are two similar things. So this particular reference may be used by the problem. Now, the solubility at the final temperature is C sub 2, allowing for any evaporation by making solute and solvent and solute balances. The equations that I'm sharing with you here is from Colson. Anyways, you have your Jan Kuplis copy and your McCabe. That way, you will also have a different resource material in this particular topic. So Jan Kuplis has a very simple material balance equation in determining the yield. And it's the same thing with your McCabe. By the way, class, excuse me. Okay, so going back, sorry about that. So if we think of yield of crystals, then that's the amount of crystals produced using material and solute balances. So we make solvent rather and solute balances to get the yield crystals for a particular crystallization process. Okay, now it has a particular formula. And when we speak of solvent balances, this is how our solvent in a particular crystallization process balance. So your W1 is your initial solvent in the liquor. Your W2 is your final solvent in the liquor. So solvent initially present in your feed to be processed in your crystallizer, and W2 is the solvent present in your final liquor. Now, Y here is the yield of crystals. In this formula, you get to see the R and the E. These are two different ratios. So the R is the ratio of the molecular mass of your hydrate. So the molecular weight or the molecular mass of your hydrate to the molecular mass of your anhydrous salt. The salt only without the water. This one with the water. So that's your R. So R is ratio of molecular mass, whereas the E here is the ratio of the solvent evaporated to the solvent present in the initial solution. Something like how much of the solvent present in your initial solution was evaporated. So this amount is expressed in terms of a ratio. So that's your E here. So you have four things that needs to be determined. That way the Y, the yield, using this particular solvent balance can be determined. So you need to know W1, W2, R, and E. That way Y can be solved. With all of those things there defined, we need also another material balance. If we did solvent balance here, we can do solute balance as well. So when we use solvent balance, this is where concentrations come in. So your C sub 1 and C sub 2 are the initial and final concentrations of your solution. Take note that if you use this particular formula, this should be the units of concentration. Mass of the solid without the water, so mass of anhydrous salt over mass of solvent only. So meaning mass of solid over mass of solvent. Now, if we work our way through with equation 1 and 2, substituting W2 from equation 1 to this equation, we will have this particular third equation. We substitute W2 from the first equation, from here. So meaning all of this here, the second and the third term here on the right will be transferred on the left. That way you will have W2. The W2 in here will be substituted in here and it will give you this one. Okay, as you can see. So the W2 was replaced by the W2 coming from equation 1. Now from here, by the way, that's an equation still that has now how many things? How many unknowns? 1, 2, 3, 4. W1, C sub 1, and C sub 2. Oftentimes, class, the C sub 1 is given. So it could be C sub 2. Your unknown could be C sub 2. The E and the R can be determined right away. So you will have just the C sub 2 as the unknown to give you the yield, if you're going to use this particular equation number 3 to determine the yield, because this E and R are simply ratios. So there's no worry about that. If there's no water evaporated, if there's no degree of evaporation, automatically this E is out of the picture. That leaves you only with the R. Okay? But there are problems, class. That is why I use caution, wherein you're going to marry. You are to merge what you have learned in evaporation and now with this. Why? Because in this case, we have problems wherein the boiling point rise of the solution in the process of crystallization is given. So, kumbaga, it's not a plain crystallization problem, but you already here incorporate what you learned regarding the boiling point rise of a solution. So in this case, class, there is a formula that will allow you to determine the ratio of the water evaporated, if there is. If the problem is silent that there is no water evaporated, then you may solve for this if it's all the information here is provided to you. Meaning, you know the lambda, which is the latent heat of evaporation of your solvent, or if there's a way for you to know this, and there's a way to know this. The Q, the heat of crystallization, should be known. The T sub 1 is the initial temperature of the solution, the T sub 2, the final temperature of the solution, and the CP, the specific heat capacity of your solution. If the amount of water evaporated is not given, you can solve for it in terms of ratio of it with the initial water in your feed to the crystallizer. However, all of this information that I have just read should be available. If not, class, if not, it's okay to assume that there is no evaporation. That, of course, it's a simple process of cooling to facilitate the growth of crystals. Now, the final formula for the yield of aqueous solutions based on this equation, if this is provided, and your equation 3 is this one. So it's now simplified. All you get to see is just the initial water in your solution, initial and final concentration, and the two ratios. Now, this formula allows you to determine the yield crystals in your crystallizer. So, whether it's an adiabatic crystallizer or a vacuum crystallizer, whether there is degree of evaporation or not, if there's none, then this E will automatically be 0. But this formula will work even if you don't have your material balance anymore. You need not do material balance for both your solid and your solvent. Now, based on the feedback of our graduates who have taken the board exam before, I don't know now with the in your case class, if I will just take a few minutes. In your case class, the board exam will really be different already than the ones that the 4th year batch now is going to get. because our graduate this year will take the board exam that is more or less similar to the board exam that was taken like 10 years ago. In a sense that the questions are just randomly generated and they are not stratified. Now, with the last meeting that was conducted by PRC, for the next set of graduates, meaning not including this year, you will have your stratified question sampling, meaning they will also get your problems generated randomly, but it will be taken from test banks in designated percentages, if I may say. So all the subjects now will be properly courses will be properly represented in terms of the problems that you are given. So what is its connection with this? Ang resulta class is at times so that a particular subject will have an application of another course. They hybridize the problems in such a way that in just one problem, they're just not hitting one course, but several courses or two courses. So it's important really to understand the fundamentals. And it's important, very important, that you know a formula that will directly, shall I say, lead you to the unknown without having you to derive it from doing material balance. I'm not saying that material balance, it will not work anymore, because if you forget, your material balance will still lead you to the same final equation. What I'm just trying to say here is that if you know a final formula and you have good memory and you can memorize it, then go use that particular formula rather than deriving it, because it will really incur time. Now, that's the same, actually, that's the same comment of our graduates then when they were reviewing already. And some review centers wherein they would comment, why will the teachers, us, referring to us, not teach us directly the shortcut? That way it will save us time when we answer the board exam. From my end, and I think it's the same concern with your other teachers, we cannot teach a shortcut formula unless you know the basics that is. Because if you're simply going to memorize a formula without understanding where it came from, what if you forget that particular formula? You don't know what to do anymore because you don't know where it came from. So it's really very important that we give you the basics, but don't expect that later on when you review, your reviewer will still go back to the material balances like what we do now. Na mabalik siya sa solvent balance, kag sa solid balance, kag sa tagaan niya kamo yield. No, it will simply give you a ready-made formula already. But where that formula came from, it's where your material balances comes in. Okay? Kay comment kina siya ya ako ano na ko nga daan nagahambal ako kay common gina nga comments ang graduates nga ang wala na lang sila kuno ginatudloan diretso sang shortcut na no offense meant, but the shortcut does not teach you the principle behind, just simply give you a formula. In my case, if you reach the subject process control, I tell my students, if we have derived a particular formula and we have already incurred time in deriving that particular formula, use that particular formula right away. Don't go back to the derivation because in the first place, it was derived for you already. It's a different thing when you're given a different system. Or in this case, it's a different thing when we're talking about really a different manner of, let's say, is there a different manner of producing crystals than this one? I think there's none. So this particular formula that is being shown to you by Colson will come in handy. So some students will write this in pencil in their handbook. Then that way, if they cannot memorize, then they will have something to go back to. But I'm not suggesting that you will write it in pencil. In our time, we do write in pencil, but we make sure that it's not as, shall I say, hindi siya balabanon. Kaya kung balanon, natikwaw na nila imo handbook, especially if the one that is proctoring you does not understand what's written there. If it's a chemical engineer, they would know that it's just simply a formula. But for others, they may think that you are cheating already. So mostly what they'll do is they'll take your handbook. And then what will happen to you if you don't have your handbook anymore? So you will be left to answer the remaining exam numbers in your exam without your handbook. And that would be very dismal. So going back to what we're saying, if you are asked for the yield, don't go back later to the problem. When you solve problems, don't go back to the solute and solvent balances that were shown to you a while ago. You may go straight to this formula. Anyway, it was derived already. If you want to practice really how this particular yield for crystals for aqueous solution came about, then you may do so when you're studying already. Write down the equation for solvent balance, write down the equation for solute balance, and check whether you come up with this particular formula for the yield. Okay, so this is still your formula for the yield, whether you use the material balance that John Kuplis will give you. But of course, class, ang kay John Kuplis, don't expect that you will have there the R and the E. Okay, it will have a different representation. Same thing with McCabe. But as I have said, if you want to use Chenku, please, if you want to use McCabe, it's fine with me. I'm just giving you a different formula here. That way you will not get used only to the two references. Okay, now we'll have this sample problem on yield of crystal. So you're given here a problem that asks for the theoretical yield of crystals which may be obtained by cooling a solution containing 1,000 kilogram of sodium sulfate, providing you with its molecular mass in 5,000 kilograms of water to 283 Kelvin. So, this is the temperature of the crystallizer already. We're going to cool it to this particular temperature. Now, this is look at this, it's 283. If 0 is 273, this is just around 10 degrees Celsius. Okay, the solubility of your sodium sulfate at 283 Kelvin is 9 kilogram anhydrous salt, so no water, per 100 kilogram of water. And the deposited crystals will consist of the decahydrate. Now, this refers already to your sodium sulfate decahydrate form, meaning the crystal that is separated from the mother liquor when your magma is processed is in the decahydrate form. Now, it may be assumed, now the last statement tells you that 2% of the water will be lost by evaporation during cooling. So the main requirement in this problem is the yield, the theoretical yield of crystals. Okay, so we will go back from time to this problem, but let's go to our board to write the solution of this. So this is our second problem, number 2. So we'll draw our crystallizer. So we'll just simply use a box here. So in here you have cooling water. And although it's not given as to the details of the cooling water, nonetheless, we'll place it there. You have this feed. There was a mention about water being evaporated. So you have B, and you have here your magma. Now this magma, when processed further, will give you the liquor and your crystals. Okay, so that's it. Our feed. Okay, let me go back to the PowerPoint. You cool a solution containing 1,000 kilogram of sodium sulfate. This is the molar mass in 5,000 kilograms of water at 283 Kelvin, or rather kilogram water to 283 Kelvin. So the preposition to here tells you that this is already the temperature inside the crystallizer. Okay, so take note of the given. We'll go back to our board. Okay, so for our feed, we have 1,000 kilogram or 1,000 kilograms of sodium sulfate. dissolved in 5,000 kilograms of water. It is to be cooled down in this crystallizer to 283. Okay, so that's it. That's the information that I get from there. It was mentioned, by the way, if I go back to that. Okay, molar mass here of sodium sulfate is 142. And so far in this particular first, you have a question here that's your given information. The solubility of sodium sulfate at this temperature inside your crystallizer is 9 kilogram anhydrous salt to 100 kilogram water. And the deposited crystal will consist of the decahydrate with this molar mass. Okay, molecular mass. Okay. So we can write here that since the solubility is mentioned, and if you got my explanation a while ago, I'll just write it here. The C sub 2, 283 K, it's 9 kilogram anhydrous salt per 100 kilogram water. If we will simplify this, this is 900 per 100, so that would then be 0.09. So with the same set of units here, I won't anymore copy that one. It was mentioned that the molecular weight of sodium sulfate is 142. And in your crystals here are decahydrate already, so meaning deca, meaning 10. So the crystals that you have here are in the form sodium sulfate, decahydrate here. Molecular weight is given to be 322. Okay, 322. Okay, there was a mention in the last statement about the amount of water evaporated. It may be assumed that 2% of the water will be lost by evaporation during cooling. So this is 2%. You will have here 2% water coming from the feed, of course. 2% of water being lost during the process of evaporation. So this is our given. And we are required for the Y. Since we have derived already the Y, there's no need for you to do balances. So we go straight to the formula of the Y that was shared to you. So your Y is equal to R W1. Okay, it's to be multiplied to C sub 1 minus C sub 2. You have here 1 minus E. And you have here 1 minus C sub 2 times R minus 1. Okay, so based on our formula, what we know and what we still do not know. So let's check. Do we know the R already? The R is the ratio of the molecular weight of the hydrate to the anhydrous, the one that does not contain water, to the hydrated and the anhydrous salt. So that would be then, so we'll make this, we'll keep that for now. Your R will be 322 over 142. This should give you 2.2676. That's for the R. For the W1 or the omega 1, when we did our solvent balances a while ago, W1 is the initial water content. So based on our given, that's 5,000 kilograms. So we'll place this to be 5,000 kilograms. Then we go to C sub 1, the concentration. So how do we express concentration here? So we express it in terms of anhydrous salt over solvent. So your C sub 1 is, how much was that? We have 1,000 over 5,000. So 1,000 over 5,000, and this should give you 0.2. Now, next, what do we see here? We have the C sub 2. Our C sub 2 is this one. The solubility, as I have mentioned to you already, it will not tell you that it's the final concentration, but the solubility of the salt based on the operating temperature of your crystallizer already tells you that that's its final concentration. So in this case, that's 9 kilograms anhydrous salt per 100 kilogram water, so that would be 0.09. So this is 0.09. So what is left is the E, the degree of evaporation. And actually, this is the ratio of the water evaporated to the initial amount. And since the problem, the way it's stated, it says here, it may be assumed that 2% of the water will be lost by evaporation. Where is this 2% coming from? So common sense will tell us that this 2% of water that will be lost from evaporation is the water from the original feed to the crystallizer. So then it is also the E. So your E now will be in the form of in decimal of that particular percentage value. So we use the E here. The E is equal to 0.02 because as defined a while ago, go back to that so you will recall. The E is the ratio of the mass solvent evaporated to the mass of solvent in the initial solution. So if 2% gets evaporated, so that's then equivalent to your E. Okay, so we go back to our board and substitute everything. So everything is in here already. All you have to do is substitute. So Y upon substitution would be something like, so we have, how much is our R? 2.227. So 2.27, we multiply it with W1, which is 5,000. There's C sub 1, which is 1,000 over 5,000. And you have in the formula here, C sub 2 times 1 minus E. C sub 1 minus C sub 2 times 1 minus E. So your C sub 2 is 0.09. 1 minus 0.02, the 2% water evaporated. Then you have 1 minus C sub 2, 1 minus 0.09, your R, which is 2.27 minus 1. Is that right? Okay, R minus 1. So that will give you a yield, which is 1,432 kilogram of sodium sulfate decahydrate. So the unit, take note of the unit. The unit now reflects the identity of the crystal, the hydrated crystal, the hydrated form of your crystal in the crystallization process. So that's 1,432 kilograms sodium sulfate decahydrate. Okay, any question here?